Everybody, in the previous video, we learned transient response characteristic or performance metrics for second-order systems. We generally concentrate on the underdamped response when damping coefficient is less than 1, but we know that some of these metrics are also useful for characterizing overdamped and critical damped systems. Okay, so let's start analyzing or remembering these performance metrics. We had rise time, peak time, overshoot, and two setting times. One is based on 2% threshold and the other one is based on 5% threshold. If we remember these formulas, they are given here. As you can see, overshoot, which depends on the damping coefficient only, which is one of the important concepts that you should remember. Setting time depends on the real part of the root. Okay, it's zeta omega n, as you can see, which is technically the time constant of also the pole. Peak time, which only depends on the damped nature frequency, which is also equal to omega n 1 minus zeta square, as you can see here. And finally, rise time is equal to pi minus phi. Phi is the angle between the complex and the real part, and omega d is the damped nature frequency. Okay, so today what we are going to do is we will solve some simple examples. Okay, so what we are going to do is we will pick a pole location, such as the one here. This is P1. We will move this pole location to a new pole location and try to understand what happens to the overshoot, setting time, peak time, and the rise time. Okay, so in this case, what we do is we keep the phi or damping coefficient, damping ratio constant. Okay, so it means that we only change the nature frequency of the system. Since, as you can see, the magnitude or the absolute value of the pole or its distance to the origin is changed, but angle is fixed. Okay, so let's start with the overshoot. As you can see, overshoot only depends on the damping ratio, which is constant, which means that overshoot is same. Okay, that's nice. Okay, so we don't change the overshoot. So in terms of transient performance and in terms of overshoot, it is fixed, but we know that something should change. Okay, let's look at the setting time. Setting time 1, okay, setting time 2, and I only wrote here the 2% setting time, but we know that the only change is 3 to 4, so nothing changed in terms of the formula. Okay, 4 divided by zeta omega m, which is the magnitude of the real part. As you can see, this is smaller than this. So what's happening is I'm technically increasing the magnitude of the denominator, which means that the setting time should drop from 1 to 2. Okay, so there's a change in performance. So which one is better? Setting time is the time that I reach a steady state threshold. So smaller the setting time, a better the performance. So here I don't have any performance change. In that case, I have an improvement in performance in terms of setting time. That's great. Okay, so let's analyze the other metrics. So what about peak time? As you can see, it's pi. Okay, it's constant, we know that, divided by omega d, and omega d is the technically damped nature frequency, which is technically equal to the projection of the pole on the imaginary axis. As you can see, from here to here, I increase omega d, which means that the peak time is also decreased, similar to the setting time. So TP2, TP1, and in general, reaching any milestone such as setting time, rise time, or peak time in a shorter time is good for transient response, which means that I'm reaching some thresholds faster, which is always good. So in that respect, the performance is also increased if I move from this location to this location. Okay, that's great. That's nice. So we have peak time improvement, we have setting time improvement. Okay, so what we have is rise time. Okay, so as you can see here, it is similar with the peak time. Pi is constant, phi is constant for this specific case. If I increase omega d, I will also increase the rise time. So in this respect, okay, as you can see, I improve the peak time, rise time performance. So if you keep the damping ratio constant, if you change the nature frequency, if you increase the nature frequency, what's happening is, except overshoot, I have a consistent performance improved. So from the transient performance perspective, if you can do that, it's better to increase the natural frequency of the system. This is the story. Okay, it's check. It's nice. Okay, now, okay, so what are we going to do? So as you can see, now it's the same thing, no problem. Okay, I just wrote the correct answers, and as you can see, everything is improved except overshoot. If we move from 1 to 2, which we did, is technically increasing the natural frequency of the system. Okay, now let's keep the natural frequency constant. Okay, so technically, which is here, j omega d is same for both P1 and P2. Okay, that's nice. So let's analyze what is changing. The phi is changing, which means that we are changing the damping ratio. Okay, the magnitude or distance to the origin is also changing. We also simultaneously change the natural frequency. Okay, we are changing both of them. But the story is, or the question is, what happens to overshoot, rise time, setting time, and peak time? Okay, that's the story, or that's the question. Okay, that's nice. So let's analyze it a little bit. Overshoot. Okay, so as you can see, overshoot depends only the tangent phi. Okay, and phi is the angle here, angle between the complex and the real part of the pole. Okay, so if I move from phi 1 to phi 2, what's happening is phi 2 is less than phi 1. Okay, so we know that tangent is monotonic with phi, which means that tangent phi 2 is less than tangent phi 1. Okay, that's great. But we have pi over tangent phi. Pi over tangent phi is less than pi over tangent phi 1. So it's not less than, it's greater. Okay, that's great. But we have a minus. So minus pi over tangent phi 2 is less than minus pi over tangent phi 1. So it's minus, since we have a larger magnitude, but it is lower in general. What's happening to overshoot is we decrease the overshoot. So in that respect, MP2 is less than MP1. It's also good to understand these trends by just looking at the extreme cases. Okay, so what's happening if I move P1 to here? It will be a purely imaginary, right? It will be undamped response, and we know that undamped response has an overshoot of 1, which is technically 100%, which is the highest overshoot you can obtain for a non-unstable system. Or it's not stable, it's marginally stable. Or if I move this pole to the infinity, what's happening is the distance, the measuring part distance will be constant, but the real part will be infinity. So it will be technically a critical damp system, which we know that the overshoot is equal to 0. So in that respect, if you keep omega d constant, and if you move your pole away from the imaginary axis, what's happening is you drop the overshoot. And in terms of good performance, this is nice. We have a performance improvement. Okay, that's great. So the story is same with the setting time. You will see that, which is even simpler. Okay, the setting time 1, because setting time depends only on the real part. Okay, so for its constant, zeta omega n, which is the distance on the real axis, is increasing. Okay, so let's clean this everything. Okay, so this is the distance 1, which is smaller than the distance 2. So I increase the magnitude of the real part, okay, which means that I drop the setting time, which is nice. We know that because we reach a steady state threshold much faster. So in terms of performance metric, there's a performance improvement. That's also great. Okay, so let's go to the peak time. Okay, T P2, T P1. Okay, that's great. Okay, so let's see what's happening here. So the peak time, as you can see, depend only the omega d, okay, which is constant, right? Okay, omega d is not changing, so we have an equality. So in terms of performance, there is no change. Okay, so I'm not changing the performance in terms of peak time, but we know that overshoot is more important than peak time because it's really the kind of the thing that we want to minimize in a transient response. Okay, so what about rise time, which is a little bit tricky, okay, because this is 2, this is 1, okay. So rise time depends on both phi and omega d, okay, but omega d is not changing, which is nice, okay. So what's happening is phi 2 is less than phi 1, okay, that's easy, but minus phi 2 is greater than minus phi 1, okay, as you can see, that's also nice, right? So omega is not changing, pi is constant, so minus phi 2 is greater than minus phi 1. So technically, if I put it like index 2, pi minus phi 2 is technically larger than pi minus 5. So in this respect, we can say that the rise time is greater in 2 than 1. Okay, let's check the result. It should be correct. Yes, that's correct. So what about performance improvement? Okay, we can say that the performance has dropped, okay, which is technically okay. But we improved overshoot, we improved the setting time, and these are the most important two of the metrics. Peak time is unchanged. There's a drop in the rise time, which seems to be bad, okay. But as I told you before, rise time is associated with the timing that's happening from the beginning to the first reach of the steady state value, but it doesn't care what's happening after that. So overall, I can say that it's still a good performance improvement, okay, overall improvement, because we have two of the most important metrics that are improved. Peak time is unchanged, rise time is dropped, but we technically don't care much in this respect. Okay, that's nice. So rise time, as you can see, let's check my also answers. It should be nice. Okay, so rise time is increased, which is slightly bad. Okay, that's nice. Okay, let's look at here. Okay, as you can see, these are consistent with our funding. Overshoot is dropped, which is good. Setting time is dropped, which is good. No change in peak time, but rise time is improved, which is slightly bad. But overall, I can say that it's good to have a pole which is like far away from the origin, even if you keep the omega d constant. Okay. So now I think we technically covered this a little bit in the previous lecture, but let's do it again. What if I keep my omega n constant, and if I move my pole from here to here, what I'm doing is I'm like driving the pole closer to the real axis or away from the imaginary axis. Okay, that's nice. I think we slightly covered this. So let's look at the overshoot. As you can see, what's happening is MP, okay, e to the power I minus pi divided by tangent phi. Okay, phi is decreasing, okay, so pi over tangent phi is increasing, but we have a minus, so in that respect I can comment on that MP2 MP1 is small, okay, which means that I have a smaller overshoot, which is always good, so in that respect the performance is improved. In this case, it's a check. I like it. It means. Okay, that's nice. So what about setting time? Okay, setting time is directly associated with the magnitude of the real part. Okay, as you can see, this distance is less than this distance. So I improve the distance of the real part, which means that I improve this part. So overall, I have a drop in setting time. And this is what I want. I want to drop my setting time. So in terms of performance improvement, I have an improved performance. That's check. Okay, so two of the most important metrics are improved. So overall, I can say that I have an improvement in performance. Okay, that's nice. Okay, no, let's keep that here. Okay, so now let's look at the peak time. Pi omega d. Pi is not changing. Omega d is changing. Okay, that's nice. Okay, so what's happening here? I'm decreasing the omega d, so it should be omega d, sorry for the mistake. Okay, so omega d is decreased, it's in the numerator, so in that respect the peak time, as you can see, is increased. Okay, so what does it mean? I have the improvement or like decrease in the performance, right? Okay, it says the performance drop. So in that respect, even if I gain in terms of overshoot and settling time, and these are certainly the most two important metrics, I still lose in the peak time. Okay, for this reason, the reason I will talk about in a second, sometimes we don't want a perfectly critical damp response. Okay, we want a little bit oscillation, not much. Okay, because we don't want overshoot, but we want to be, instead of here, we may want to stay a little bit in this location. Okay, such that we don't lose much in terms of peak time and the rise time. And let's talk about the rise time, which will be a little bit tricky. Okay, so what's happening is phi is decreasing, right? Pi minus phi divided omega d. Okay, so phi is decreasing. Okay, so because of the minus phi, numerator is increasing. There is an increase in the numerator. Omega d is decreasing. Okay, but overall, as you can see, rise time is also, okay, tr2, tr1 is increasing. And let's check my result. As you can see, it is true. Okay, in that respect, performance is dropped. Okay, so if I'm democratic, okay, or if I technically don't care about the meanings of these metrics, I can say that two of the metrics I have an improvement and two of the metrics I have a decrease in performance. So overall, I'm on average. Okay, so it's not exactly true. Okay, so and if you look at the extremes, you can understand that, because first of all, if you are very close to imaginary axis, it's too bad because you are on the edge of stability anyway, which is bad. Okay, and if you are here, it's critical. Now we know that it's the best settling time, no overshoot, right? And overshoot and settling time are certain two important metrics. So overall, I can say that there's an improvement in performance. Okay, that's nice. But in this case, if you're just limited to the case when you change the natural frequency, okay, if you talk about like, okay, sorry for that, points that are really like here and here, of course, there's an improvement in performance. But if you are close to real axis, if one of pole here, if one of the pole here, you may still want, it depends on the application, of course, this pole. But if you are here and if you want to go here, this is certainly good, always, because you are also technically avoiding the edge of stability, because if you pass to this region, it will be unstable. So overall, I can say that there's an improvement in performance if you keep in this direction. Okay, and of course, if you keep the natural frequency constant, that's nice. Okay, as you can see, this is the same story. Okay, the rise time, not improvement, peak time, net improvement, or should it improvement, settling time, as you can see, it is also improved. Okay, and later we will solve numerical answers, and that in that respect you will better understand my comments. Okay, now it's a more straightforward story. I keep the real part constant, okay, which means that I'm keeping zeta omega n constant. So I'm moving from 1 to 2 in this direction. What I'm doing is I'm increasing the damp nature frequency by keeping everything constant, which means that real part. Okay, so in that case, the story is more monotonic and simple. You will see that. Okay, so MP1 and MP2. Okay, that's great. So MP1 depends on the tangent phi. Okay, that's nice. This is phi 1. This is phi 2. As you can see, I increase phi 2. I increase the angle. So which means that I decrease the damping. Overall, you can see that based on the same story, I increase the overshoot. Okay, so let's talk about the extremes. Okay, this extreme is when there is no angle, there is no damp nature frequency, there is no overshoot. If you go in this direction, the maximum overshoot is 100%, because it will look like a purely imaginary system. Okay, so that's nice. Okay, so I have a bad response in terms of overshoot. It's bad, right? In terms of performance, it's really bad. Okay, I want my overshoot to be as small as possible. Okay, what about settling time? TS1, TS2, it depends on the sigma, so it's the same. So in terms of performance, I have no change. Okay, that's great. So let's look at the peak time, which is also straightforward. TP2. So pi divided by omega t. Omega t is increasing, so peak time is decreasing. Okay, I think it's not that monotonic, right? So I have a peak time improvement. Okay, so what about the rise time? Okay, so rise time. So as you can see, it's the same story. Okay, omega d is like increasing, so I'm decreasing the rise time. Phi is increasing, but it's minus. It's the same effect. So I have like this. Okay, I have a performance improvement. So from this perspective, I have two checks. One no change. Okay, one bad. Okay, so it means that it wins. So it's good to have a high oscillation, a high frequency oscillations, which is correctly not true. Okay, or not always. Okay, it's the same. In general, this is still bad because you are losing from the most important metric, overshoot. Okay, setting time is not changed. That's nice. You are gaining the peak time and rise time. Okay, but the story is similar. Okay, if you are really away, okay, if one pole is here, let's change the color. Okay, so let's do that. If one pole is here and if other pole is here, there's a huge gap between these locations, so overshoot will be too bad in this case, very good in this case. So in that case, you should pick this. Okay, but sometimes, as I told you before, if you are perfectly critical damped, okay, your overshoot is 0, but here it's maybe like in terms of percentage, just 5%. Okay, it might be small, or even 2% or 1%. It's small overshoot. Setting time is same, but you can really gain a lot in terms of rise time if you move a little bit to the oscillatory region. Okay, so categorically avoiding the oscillations may not be a good idea for all of the applications or all of the systems. But these trends are like absolute. Okay, so if I ask you that what happens to overshoot, as you can see, it is like getting worse. Setting time is same. Peak time and rise time is improved in this case. Okay, so that's everything I want to talk about in this simple illustrative examples. What we did is we technically characterized what happens to these performance metrics if I move my location in some specific directions.